Tonight, you are arriving at a moment that astronomers have quietly been waiting for all year. A moment when the universe has opened a final, fleeting window into our nearest galactic neighbor. It is November 2025, and for the first time in human history, you are living in a world where the Andromeda Galaxy has been mapped more completely than any galaxy outside our own. Not a single image, not a mosaic stitched together for textbooks, but a full reconstruction built across every wavelength we can reach. Optical light, infrared glow, radio emission, and the soft gravitational signatures that move through space like ripples in a vast, silent sea. This is the last complete picture we will have before the next generation of models begins rewriting everything we think we know in 2026. And the timing is not a coincidence. You clicked on this video because the title spoke to a part of you that still looks up at night and wonders what is coming next. You want clarity. You want calm. And after a long year, you want something real to settle your mind before sleep. Something bigger than work, bigger than stress, bigger than anything waiting for you tomorrow. And tonight, that something is Andromeda. You are here because you've heard pieces of the story before. That Andromeda is 2.5 million light years away. That it is a spiral like our own. That one day, long after any of us are gone, it will merge with the Milky Way. But this year, astronomers found details they did not expect. Details released only weeks ago that changed the tone of every discussion about our galactic neighbor. In late 2025, the new data revealed structures inside Andromeda that appear sharper, stranger, and more organized than any previous map had suggested. Imagine a galaxy so large that 1 trillion stars drift through it like embers carried on an endless wind. Now imagine seeing that galaxy not as a smudge of light in the sky, but as a living system, full of hidden currents and patterns you could never see before. That is what this new data offers. A final window before the next year brings new simulations and interpretations. A last chance to look at Andromeda as it is today, before we begin seeing it in entirely new ways. And that is why you are here. Because you want to know what changed, what was discovered in these new images, why some astronomers are calling 2025 the most revealing year in the history of studying Andromeda, and why this calm, distant galaxy suddenly feels closer than ever. As you listen, imagine yourself standing beneath a quiet sky. The noise of the world fades until all you can hear is the soft hum of your own breath. Above you, Andromeda rises, not as a faint blur, but as a presence. A great lantern of stars drifting through the dark, carrying the memory of ancient collisions and the promise of things yet to come. The light reaching you now left that galaxy when early humans first lit fires against the cold. And yet it arrives this year with new meaning, because for the first time, we can see almost everything it contains. We can see the twisted dust lanes that hide star-forming regions. We can see the streams of stars left behind by galaxies Andromeda once consumed. We can see the smooth rotation of its core and the faint glow surrounding its central black hole. But we can also see something that raised eyebrows across observatories worldwide. Around Andromeda, many of its satellite galaxies are aligned in a plane so flat so clean that it challenges the way we think galaxies organize themselves. It is the kind of discovery that makes scientists pause, lean back, and ask quietly, how long has this been here, waiting for us to notice? You are listening because you want a moment to breathe, but you also want that sense of discovery. That feeling you had when you were younger, when space still felt endless, mysterious, and entirely beyond you. You want to feel that again, without the noise of modern life pulling at your attention. Tonight, you will. You are stepping into the calmest, clearest view of Andromeda humanity has ever had. You will travel from its ancient past to its distant future, from the nights when it was mistaken for a simple cloud to the recent days when new observations reveal structures that no model can fully explain. You will move through its stars, its scars, its dust, and its gravity, and you will understand why 2025 is the perfect moment to take this journey. And best of all, you will travel slowly, gently, at a pace that lets your mind settle and drift. Because the universe does not hurry, and neither should you. You are here to learn, but also to rest. And tonight, as you float beside this great spiral in the dark, the questions that brought you here will finally begin to take shape. By the end of this night, you will know why astronomers say that Andromeda is not just a galaxy we study. It is a galaxy that is calling us forward. For more than 2,000 years, Andromeda was nothing more than a soft blur in the night sky. If you were standing under the darkness with the early astronomers, you wouldn't see a galaxy or a structure or anything with depth. You would see a faint, hazy smudge, just bright enough to notice, just mysterious enough to linger. A whisper of light that didn't behave like a star and didn't quite look like a cloud. Something in between, something undefined. For centuries, that faint glow was cataloged again and again as a nebula, a cloud, a mist, a wandering patch of fuzz that drifted across old star maps. Long before the age of telescopes, observers saw it as a harmless curiosity. Even when early lenses made it clearer, it still seemed too small, too delicate, too ghostly to be anything grand. It sat quietly in a corner of the night sky, almost easy to miss, especially if you weren't looking for it. And so the name Andromeda Nebula held on for generations. It fit what people thought they knew. It fit the universe they believed they lived in. Because in the early 20th century, nearly every astronomer agreed on one fundamental idea. The Milky Way was the entire universe. It wasn't just our home galaxy. It was everything. All of space, all of existence, all of creation in one vast star-filled island. And if the Milky Way was everything, then anything we saw in the sky had to be inside it, including Andromeda. But a quiet tension was building beneath the surface. More and more astronomers began noticing things inside the so-called Andromeda Nebula that didn't behave like structures within the Milky Way. Some novae inside it appeared unusually faint, far dimmer than novae inside our galaxy. Something wasn't adding up. Something about that blur didn't fit the model. By 1920, the questions had grown loud enough to spark one of the most important scientific confrontations of the century, a debate that would reshape human understanding of the cosmos forever. Today, it's remembered simply as the Great Debate. On one side stood Harlow Shapley, a brilliant astronomer who had spent years mapping the size of the Milky Way. Based on his calculations, The galaxy was enormous, so enormous that there was no room left for anything else outside it. If the Milky Way was that big, then Andromeda had to be inside it. It couldn't be a separate entity. It had to be a local cloud, a cluster, or some strange internal structure we didn't yet understand. On the other side stood Heber Curtis, a man who stared directly at the faint novae inside Andromeda and felt something was off. These novae were too dim to be inside the Milky Way, too distant, too isolated. Curtis argued that the only explanation was that Andromeda wasn't a nebula at all. It was a full galaxy, a separate island universe far beyond the edge of our own, a world containing its own stars, its own dust, its own mysteries. Andromeda is an island universe, he said, and those words carried a weight that echoed far beyond the lecture hall. During the Great Debate of 1920, both men laid out their evidence with passion and precision. Shapley argued scale. Curtis argued distance. Shapley described a Milky Way so vast it swallowed the sky. Curtis described novae so faint they must be millions of light years away. Each argument was powerful. Each one revealed the limits of what humanity understood at the time. And in the end, no one declared a winner. Not that night, not that year. The evidence simply wasn't complete enough. The universe was holding back one last piece of the puzzle. That final piece arrived in the mid-1920s when a young astronomer named Edwin Hubble pointed a powerful telescope toward the heart of the Andromeda Nebula. Using the light of Cepheid variable stars, stars that brighten and dim with a predictable rhythm, Hubble measured their distance with a precision no one had achieved before. And the result was staggering. Those stars were far, far outside the Milky Way. So far, in fact, that Andromeda could not possibly be inside our galaxy. It wasn't a cloud. It wasn't a smudge. It wasn't a nebula. It was an entire galaxy on its own. A galaxy millions of light years away. A galaxy larger than the Milky Way. A galaxy racing toward us through the dark. When Hubble published his findings, the scientific world shifted overnight. You can almost imagine the silence in observatories as astronomers read his paper for the first time. Here was the proof. Here was the key. Here was the moment that cracked the universe open. The Milky Way was not the universe. It was one galaxy among many. And if Andromeda existed, then the night sky must be filled with countless others. Billions, maybe trillions. In that moment, everything changed. Human beings went from living in a single galaxy universe to a universe filled with endless worlds. The scale of reality stretched outward into a horizon so vast that even now, a century later, we struggle to comprehend it. Andromeda became more than a smudge. It became a landmark, a turning point, the first great door into a deeper cosmos. As a viewer tonight, someone who knows what it feels like to look up at the sky and want both truth and peace, you are standing right where Hubble stood. You are about to see the galaxy as he saw it. Not as a cloud, but as a world with structure, history, and depth. A world that proved we are part of something far larger than we ever imagined. Now that we know what Andromeda truly is, we can finally explore what it contains. If you were able to drift toward Andromeda tonight, crossing the silent gulf between galaxies, the first thing you would notice is its shape. From a distance, Andromeda spreads out like a great cosmic pinwheel, a vast barred spiral galaxy with a bright central core and sweeping arms made of dust, stars, and gas. It resembles the Milky Way in many ways, yet everything about it feels just slightly bigger, slightly brighter, slightly more forceful, as though it has lived a louder, more restless life than our own galaxy. Andromeda stretches across more than 220,000 light years, almost twice the width of the Milky Way. Its mass, too, sits at the upper end of what spiral galaxies can be, containing roughly 1 trillion stars, hundreds of billions more than the stars that light our home galaxy. When you look at it in images, the scale is hard to hold in your mind. Every bright patch contains clusters of thousands of stars. Every faint line hides clouds larger than anything we can imagine. Even the dark gaps are not empty. They are rivers of cold dust waiting quietly in the shadows. What's even more surprising is how quickly Andromeda spins. Despite being larger and more massive than the Milky Way, it rotates at comparable speeds, and in many regions, even faster. Stars closer to its center complete orbits in shorter cosmic timescales than expected, as though the galaxy carries a deeper gravitational pull in its heart. That extra speed hints at something hidden beneath the visible stars, something we'll explore in later parts. But for now, it tells you this: Andromeda is not a gentle, slow-moving spiral. It is a dynamic engine of motion, a galaxy that has been shaped by its past and continues to evolve with powerful momentum. To understand this galaxy properly, it helps to break it into its major components, just as astronomers do. At the center sits its bulge, a dense sphere of old red stars that formed billions of years ago when the galaxy was young and turbulent. These stars are ancient survivors, relics of the earliest era of Andromeda's history. If you could stand within that region, the sky would be dense with light, with stars glowing so closely together that the night might never fully darken. Surrounding the bulge is the disk, a thin, wide expanse where the galaxy's spiral arms unfurl like ribbons of starlight. This is where the action happens. Young, blue stars ignite along the arms, forming in clusters where clouds of hydrogen collapse under their own gravity. In these bright regions, the galaxy feels alive, renewing itself continually. These fire-forged stars burn hot and fast, living brilliant but brief cosmic lives, before fading, exploding, or dissolving into the interstellar medium. Hydrogen gas flows through the disk like slow-moving rivers, drifting, cooling, and occasionally collapsing into new suns. In some places, the gas forms delicate filaments. In others, it gathers into massive clouds large enough to give birth to entire clusters. Every bright knot in the spiral arms marks a place where gravity pressed gas together until new stars flared into existence. And in every dark hollow, dust lanes weave through the arms, breaking the light into patterns and shapes that add texture to Andromeda's swirling form. These dust lanes play a quiet but powerful role. They hide regions of starbirth from visible light, forcing astronomers to turn to infrared imaging to see through them. Without infrared telescopes, huge sections of Andromeda's structure would remain invisible, like chapters torn out of a book. Through infrared, those hidden areas bloom into view. Vast nurseries where hundreds or thousands of stars are forming at once, shielded from our eyes by curtains of cold, dark dust. The halo of Andromeda extends far beyond the visible disk, reaching almost 1 million light-years into space. This vast faint sphere contains old stars, clusters, and the remnants of galaxies that Andromeda consumed long ago. And this is one of the most fascinating features of its structure. Andromeda is a stellar cannibal. It has grown not only by making stars, but by absorbing smaller galaxies that wandered too close. You can see evidence of this in the stellar streams that curve around the galaxy like faded scars. These thin trails of stars stretch outward in great arcs, telling the story of dwarf galaxies that were pulled apart and folded into Andromeda over billions of years. Some streams wrap around the galaxy multiple times, like ribbons left behind by ancient collisions. Others fall inward, feeding the bulge or dissolving into the halo. Each one is a footprint of a smaller world that no longer exists. Disrupted gas clouds reveal the same history. Clouds that once belonged to other galaxies now drift through Andromeda's outskirts, twisted into shapes that make their origins clear. When astronomers map these clouds, they find patterns that don't align with the galaxy's natural rotation, evidence that they came from elsewhere, carried in by long-vanished companions. Star clusters are also abundant in Andromeda, far more numerous than those in the Milky Way. Some are young, burning with hot blue stars. Others are extremely old, older than many of the structures in the galaxy itself. These ancient globular clusters are leftovers from the galaxies Andromeda consumed, preserved like fossils that drift through the halo. Their motions and compositions offer clues about the galaxy's violent history, helping astronomers piece together the sequence of mergers that built the massive spiral we see today. All of this makes Andromeda both familiar and foreign. It looks like the Milky Way, yet everything inside it is turned up slightly. Brighter, faster, larger, more dramatic. And as you begin to understand its structure, you start to see a pattern in its history. A galaxy this large didn't grow by accident. It grew because it survived collisions. It grew because it devoured smaller galaxies. It grew because gravity shaped it across billions of years. Galaxies grow by eating smaller galaxies, astronomer Sandra Faber once said. And nowhere is that truer than in Andromeda. As you take in the scale of this structure, with its swirling arms, its ancient core, its restless gas, and its drifting streams of stars, you can feel the galaxy's past moving through you. And you realize that this journey is only beginning. For everything we see, the bright stars, the glowing arms, the old clusters, tells only half the story. But the visible stars are only half the story. If you were to drift above Andromeda and look down at its glowing arms, its star-forming regions, and its shimmering clusters, you might feel for a moment that you understand the galaxy. You see the light. You see the motion. You see the structure traced by dust and gas. But the truth is that almost everything you're looking at is only a thin layer on the surface of something far larger and far stranger. The real Andromeda, its true shape, its true mass, its true power, lies mostly in the dark. Astronomers realized this when they measured the way Andromeda spins. If you could follow the stars that orbit its center, you would expect them to slow down as they move outward, the way planets do in our solar system. But they don't. Stars near the edges of the galaxy move far too quickly, racing along their orbits with a speed that should fling them into intergalactic space. They should be escaping. They should be gone. And yet, they remain bound, held in place by something we cannot see. To keep those stars from flying away, Andromeda would need far more mass than the stars, gas, and dust we observe. Something invisible must be adding gravity. Something massive. Something everywhere. That something is dark matter. Imagine the luminous disk of Andromeda, the part you can actually see, as a small coin resting inside a vast transparent balloon. The coin is beautiful, textured, bright with detail, but almost all the weight is in the balloon. That balloon is the dark matter halo, a spherical structure that surrounds the entire galaxy, stretching nearly 1,000,000 light-years across. It is so large that if you could place Andromeda's visible disk at its center, the glowing spiral would look tiny compared with the halo holding it together. This halo is not empty. It is built from particles we cannot detect directly, particles that do not emit light, absorb light, or reflect light. The only reason we know the halo is there at all is because its gravity shapes everything Andromeda does. It determines how fast stars orbit, how gas collapses into new suns, how satellite galaxies move, and even how the galaxy will collide with our own far in the future. When Andromeda and the Milky Way eventually come together, their glowing disks will interact, stretching, twisting, distorting. But the visible interaction will be nothing compared to what happens in the dark. The two enormous halos will pass through each other like ghostly oceans, overlapping, blending, and finally settling into a new shape that defines the architecture of the merged galaxy. Long before the stars collide, long before the spiral arms tear or reform, the dark matter halos will have already determined the destiny of everything inside them. This is why astronomers say that galaxies are not built from stars. They are built from halos. The light is decoration. The structure is invisible. And yet, even though we cannot see dark matter, we can map its shape. When light from distant galaxies passes near Andromeda's halo, gravity bends it slightly, a subtle distortion called gravitational lensing. By measuring those distortions across the sky, like tiny ripples, scientists discovered that the halo is not smooth. It is clumpy, lumpy, filled with small concentrations of dark matter packed together in ways we still don't understand. These clumps may be the remains of dwarf galaxies Andromeda absorbed. They may be natural fluctuations from the time the universe was young, or they may be signatures of dark matter interacting with itself, something no one has ever observed, but many scientists are now considering. The mystery only deepened in 2025, when new observations suggested that the halo might not be behaving as a perfectly collisionless fluid. Some regions appear thicker, heavier, or more distorted than expected, raising the possibility that dark matter particles might collide or interact under certain conditions. If dark matter can interact with itself, even weakly, it would change the way galaxies form. It would change the timeline of the universe. It would rewrite every model we use to describe cosmic evolution. This is why laboratories around the world spent the year running experiments to test for something called dark matter self-interaction. Most results are preliminary, but the idea alone is enough to make astronomers step back and wonder whether the universe is far stranger and far more alive than we thought. Most of the universe is missing, but its gravity is not, Vera Rubin once said, and her work remains the foundation of everything we know about dark matter today. She was one of the first to measure the strange rotation curves that revealed galaxies like Andromeda are wrapped in enormous halos of invisible mass. Her discovery didn't just change astronomy, it revealed that the cosmos is built on a hidden scaffolding. Tonight, as you sit with these ideas, there is something quietly thrilling about knowing that 90% of Andromeda is invisible. You are looking at a galaxy whose true body is hidden behind a veil of silence. A galaxy whose skeleton is made of something we have never touched, never seen, and cannot describe. Yet it holds together a trillion stars with invisible hands. You came here to understand Andromeda, and in doing so, you are learning the deeper truth about galaxies everywhere. Light shows us beauty, gravity shows us structure, and dark matter shows us the unseen forces that shape both. 90% of Andromeda cannot be seen, but without it, nothing in the galaxy, not a star, not a cluster, not a single orbit, would make sense. And now that you've glimpsed the invisible skeleton, you are ready for the heart of the galaxy itself. If dark matter shapes the galaxy, the black hole rules its heart. At the center of Andromeda, buried beneath layers of stars and dust and ancient light, lies an object so massive and so commanding that it dictates the motion of everything around it. You cannot see it directly. You cannot watch it shine or flare or glow. Yet its presence shapes the galaxy with silent authority. Astronomers call it M3, the supermassive black hole at the heart of Andromeda, and it is one of the most powerful structures in the entire local group. If you were able to drift close to this core, you would see something extraordinary. A dense nuclear star cluster orbiting a point of gravity so intense that no light can escape it. Thousands of stars crowd the region, many of them whipping around the center with unbelievable speed, following paths curved by an invisible force. Everything here feels compressed, accelerated, sharpened. It is a realm where motion itself bends under the weight of mass. M31 contains about 140 million times the mass of our Sun. To put that into perspective, Sagittarius A, the black hole at the center of the Milky Way, contains only around 4 million solar masses. That means Andromeda's central black hole is roughly 35 times more massive than the one in our own galaxy. And that difference is not random. It carries a story. Astronomers believe M31 became so massive because Andromeda has collided with and absorbed many smaller galaxies over billions of years. Each time a dwarf galaxy spiraled in, it likely carried its own central black hole. Over cosmic time, these black holes merged, feeding the growth of M31s until it became a true giant. Andromeda's violent past is written not only in its stellar streams, but in the immense size of the object that sits at its core. Even now, long after those collisions subsided, the signs are still visible. Stars near the center of Andromeda travel at extreme velocities, some moving at hundreds of kilometers per second. Their orbits are tight and frantic, like sparks spiraling around the drain of a cosmic whirlpool. The only explanation is the gravity of the supermassive black hole they circle. Every path, every acceleration, every burst of motion confirms that M31 Rose dominates this environment. Yet for all its power, M31 Rose is currently quiet. Unlike the black holes you see in artist illustrations, erupting with jets or glowing with swirling disks of gas, M31 is in what astronomers call a quiet mode. Very little material is falling into it, which means it doesn't produce the brilliant radiation or dramatic flares that active black holes are known for. It sleeps, heavy and silent, like a furnace that is burned low, but still holds immense heat beneath the surface. But even a sleeping black hole can awaken. As Andromeda continues to move through space, stars drift, gas clouds wander, and debris from past collisions settles into new orbits. At some point in the far future, something may fall too close to M31. A gas cloud, a disrupted star, or a cluster passing through the wrong corridor. When that happens, the black hole could flare back to life. The quiet core could ignite again, emitting radiation as matter spirals inward, heating to millions of degrees before crossing the event horizon. Astronomers cannot predict when such reactivation might occur, only that it is inevitable. Black holes grow, they feed, and waiting is part of their nature. And M31 may not be alone. Based on the galaxy's merger history, many astronomers suspect that Andromeda still contains a population of intermediate mass black holes, objects too small to dominate the core, but too large to be ordinary stellar remnants. Some may orbit in the halo. Others may drift between star clusters. A few may hide deep in the disk, dark and unlit, influencing the motion of stars around them in subtle but measurable ways. Even stranger is the possibility of wandering black holes left behind by past mergers. When galaxies collide, their black holes do not always sink cleanly into the center. Some are slingshotted out of their orbits, left to roam through the outer regions of the galaxy. These wanderers drift silently, without light and without warning, like invisible glaciers carved from pure gravity. Finding such black holes is almost impossible through direct observation. But gravitational lensing offers a way. When a black hole passes in front of distant stars, its gravity bends their light. The effect is tiny, but it can be measured. In recent years, astronomers have used this technique to discover lone black holes in the Milky Way. And now, similar gravitational distortions in Andromeda hint that more may be hiding there too. When you study black holes, Andrea Ghez once said, you realize they are not monsters, they are engines. Engines that compress space and time, engines that shape galaxies, engines that drive some of the most extreme processes in the universe. And nowhere is that more apparent than in Andromeda, where the central engine is massive enough to shape the motion of millions of stars and old enough to carry the scars of long-forgotten collisions. As you take in this hidden world, you can feel the gravity of the place, not just physically, but emotionally. A supermassive black hole carries a kind of solemn authority. It commands without speaking. It shapes without revealing itself. It is the quiet master of a galaxy that has lived through chaos and emerged stronger for it. And in the far future, when Andromeda merges with the Milky Way, M31 Hoth may meet Sagittarius A in a dance so powerful that space-time itself will shudder. Some simulations suggest the two black holes will spiral toward each other, merging into a new, even more massive core. Others suggest one may be flung outward, becoming a wandering black hole in the merged galaxy. Whatever the outcome, the end result will define the heart of the galaxy we will one day call home. Everything in Andromeda, from the swirling arms to the ancient halo, is influenced by this colossal gravitational engine. And around this engine, Entire communities of stars are born, evolve, and sometimes disappear. When you look at Andromeda from afar, you see light, but when astronomers look closer, they see something much more revealing: a chemical code written into every star, every cloud, every cluster, and every filament of gas. This code is what scientists call a chemical fingerprint. It is the pattern of elements forged in earlier generations of stars, carried forward into the next, and preserved like a memory in the composition of the galaxy. And just like a human fingerprint, no two galaxies carry exactly the same one. The story begins with the universe's simplest building blocks. Hydrogen and helium, formed in the first 3 minutes after the Big Bang, make up most of the atoms in Andromeda. These elements are ancient, untouched relics from a time before the first stars ever ignited. But everything heavier, from carbon to oxygen to iron to nickel and silicon, came later. These heavier elements were forged in the hearts of massive stars, created under intense pressure and heat, then scattered into space when those stars exploded or shed their outer layers. Every new generation of stars forms from the leftovers of the stars before it. That means the chemical composition of a star tells you something about when it formed, where it formed, and what kind of stellar ancestors came before it. In this way, a galaxy holds its own biography within its chemistry. In Andromeda, the contrast between old and new is striking. The halo, the wide, faint sphere of stars stretching far beyond the visible disk, is filled with old, metal-poor stars. These stars contain very few heavy elements, which tells astronomers that they were born early in the life of the universe. Their light carries the signature of a time when only the first generations of stars had lived and died. They shine with a simplicity that feels ancient, almost primitive, like old artifacts preserved in the sky. Near the spiral arms, though, the story changes. There, young stars burn bright with heavy elements. These regions are rich in oxygen, carbon, iron, and more, evidence of countless cycles of star birth and star death. The spiral arms are bustling, chemical-rich neighborhoods built on the ashes of their ancestors. Compared with the halo, they are modern, complex, and energetic. This contrast alone would be enough to show that Andromeda has lived through turbulent times. But spectroscopy, the science of splitting light into its purest colors, reveals something even more intriguing. When astronomers examine the isotopes in Andromeda's stars, they find patterns that don't fully match those of the Milky Way. Isotopes are variations of the same element with different numbers of neutrons, and their ratios act like timestamps. They reveal how many massive stars lived in a region, how quickly those stars formed, and how violently they died. In Andromeda, certain isotopic ratios, especially in carbon and oxygen, don't align with standard models. They differ from what we see in the Milky Way, suggesting that Andromeda's early history was shaped by different conditions. Perhaps it had more massive stars. Perhaps it formed them faster. Or perhaps it collided with galaxies whose chemical stories differed dramatically from its own. And that brings us to one of the most fascinating discoveries in recent decades. Some outer regions of Andromeda carry chemical signatures that don't belong to it at all. Star clusters and stellar streams in the far halo contain ratios of elements that match the profiles of small, ancient galaxies. These galaxies must have been devoured long ago. Their remains were pulled apart, scattered, and folded into Andromeda's halo. And yet their chemistry endured. Even after billions of years, the stars they contributed still whisper the history of where they came from. This is one of the reasons spectroscopy is so powerful. It doesn't simply tell you what a star is made of. It tells you who its ancestors were. It tells you which galaxies merged. It tells you which clusters survived long enough to carry their chemical signatures into the present. And in a galaxy as active as Andromeda, those signatures are everywhere. Cold molecular clouds, the birthplaces of new stars, contain carbon monoxide, an indicator that gas is cooling and condensing. Regions rich in heavier elements show that many generations of stars have lived and died there, enriching the galaxy with each cycle. In other places, the lack of heavy elements reveals untouched fragments of the early universe. The diversity is remarkable. Some regions sparkle with metal-rich stars, while others look chemically frozen in time. The deeper astronomers look, the clearer the pattern becomes. Andromeda is chemically uneven. Its composition varies not just from center to edge, but from arm to arm, cluster to cluster, and stream to stream. It is a patchwork galaxy, stitched together by mergers, collisions, and ancient disruptions. Every part carries its own version of the story. Every region has lived a different life. And this unevenness, this chemical complexity, is one of Andromeda's defining strengths. In quiet galaxies, chemistry is smooth, predictable, almost monotone. But in Andromeda, the variety of elements and isotopes shows a turbulent, active past, a past where many galaxies collided, many stars lived and died, and many environments mixed into one. It is, in a way, a timeline written in atoms, a chemical evolution charted across billions of years, a biography told through the ingredients of stars. Every galaxy carries the memory of its past in the chemistry of its stars, Carl Sagan once said. And standing here with Andromeda in view, you can feel the truth of that. Its light is beautiful, but its chemistry is honest. It tells the stories that gravity and motion alone cannot. You came here to understand Andromeda more deeply, and now you know that its identity is not just shaped by its structure or its motion, but by the elements within it. Hydrogen remembers the beginning. Heavy elements remember the generations of stars that burned before us. Isotopes remember the galaxies that merged and disappeared. Together, these elements form a mosaic far richer than anything the eye alone can see. And as the chemistry leaves its clues across the galaxy, the stars themselves reveal the rest. When you drift deeper into Andromeda, past the glowing arms and the quiet haze of ancient clusters, you begin to encounter stars so unusual that they feel almost impossible. These are not the calm, familiar stars like the sun. These are extremes. Objects that stretch the boundaries of physics, erupt with unpredictable power, or drift through the galaxy with speeds that defy reason. In Andromeda, these strange stars are not rare accidents. They are signposts of a galaxy that has lived a long, complicated life, shaped by collisions, starbursts, and cycles of creation and destruction. One of the first kinds you encounter are the luminous blue variables, or LBVs. These stars are among the most radiant objects in any galaxy. They shine with such overwhelming brightness that even from millions of light years away, they stand out like sparks on a dark ocean. But their brilliance is unstable. LBVs can brighten or dim erratically, sometimes changing their luminosity by several magnitudes in a matter of months. They are stars on the edge of catastrophe, giants in the final stage before exploding as supernovae. Andromeda holds several LBVs, but one in particular has fascinated astronomers for decades. AE Andromeda. This star refuses to behave predictably. Its brightness shifts without warning, rising and falling in patterns that resemble breathing. At times, it swells to extraordinary luminosity, then retreats again into relative quiet. These cycles tell astronomers that AE Andromeda is burning through its fuel in a turbulent, unstable way, shedding its outer layers and preparing for a future that will likely end in one of the most powerful explosions the galaxy can produce. Near these LBVs, another class of exotic stars flickers with intense heat, Wolf-Rayet stars. These stars are enormous, hot, and extraordinarily short-lived. They have shed their outer layers of hydrogen, exposing the helium-burning cores beneath. Because of this, a Wolf-Rayet star glows with a fierce, almost ghostly light. Their spectra reveal powerful stellar winds ripping away matter at incredible rates. In Andromeda, these stars appear primarily in regions where new stars are forming at rapid speeds. Their presence tells astronomers that the area around them is young, energetic, and chemically rich. If LBVs and Wolf-Rayets represent instability and intensity, then hypervelocity stars represent motion pushed to the extreme. These stars blaze through Andromeda at speeds so high that some of them may eventually escape the galaxy entirely. Imagine a star cast out like a stone slung from a cosmic slingshot. Some hypervelocity stars are launched by the explosion of a companion star. Others are flung outward by interactions near M31s, accelerated to such speeds that they break free from Andromeda's gravitational pull, heading into the dark between galaxies. To picture this, imagine a star racing away from the core at more than 1,000 kilometers per second. Its orbit bends outward, stretches, and then snaps open completely. At that moment, the star becomes a wanderer. It will drift through vast regions of space where no galaxy dominates the sky, carrying with it the chemical story of its birthplace. The idea that stars can be thrown out of galaxies, not gently, but violently, is one of the strange revelations that makes Andromeda feel alive. Not all rare stars in Andromeda are fast or luminous. Some are quiet in comparison, but just as important in the story of the galaxy's evolution. Carbon stars, for example, glow with a deep red light caused by large amounts of carbon in their atmospheres. These stars form late in their lives, dredging up carbon from their interiors and releasing it into space through gentle stellar winds. Over time, carbon dust from these stars enriches the interstellar medium, creating the raw material for new stars, new planets, and possibly even the complex chemistry that leads to life. Their contribution is subtle, but without them, galaxies would lack many of the ingredients needed to build worlds. Deeper inside the galaxy, you encounter stars far stranger than carbon-enriched giants. Magnetars, some of the most extreme objects in the universe, reside here as well. These neutron stars possess magnetic fields trillions of times stronger than Earth's. When they flare, they release bursts of X-rays and gamma rays, powerful enough to be detected across enormous distances. A magnetar's magnetic field is so intense that it can distort atomic structures, twisting matter into shapes that could not exist anywhere else. The mere idea of such an object existing inside Andromeda adds a sense of awe and unease to the journey. And then, in the quieter regions of the disk, clusters of white dwarfs drift through the galaxy, many of them variable. These white dwarfs pulse gently or brighten when accreting material from companion stars. Some of these interactions can lead to nova events, brilliant outbursts caused by runaway nuclear reactions on the surface of a white dwarf. Each nova leaves behind chemical traces, adding fresh material to the interstellar medium, continuing the cycle of destruction and renewal that drives the evolution of Andromeda. Every one of these rare stars plays a role in telling the story of the galaxy. LBVs and Wolf-Rayet stars announce regions where massive stars are forming and dying. Hypervelocity stars trace the gravitational interactions of the core. Carbon stars enrich the galaxy with the dust needed to build planets. Magnetars show where extreme stellar remnants exist, revealing regions shaped by past supernovae. Variable white dwarfs mark the locations of binary systems locked in slow, steady exchanges of matter. Together, these strange stars create a portrait of a galaxy that is far from uniform. They show that Andromeda is not a smooth, quiet spiral, but a place filled with extraordinary environments. Some areas are ancient and metal poor. Others are dense, hot, and bursting with activity. Still others contain stellar refugees or relics from long-forgotten collisions. This variety is a reminder that galaxies are not static. They are dynamic ecosystems shaped by time, gravity, and the death and rebirth of stars. To study strange stars is to study the extremes of nature, Kip Thorne once said, and these extremes give Andromeda its character. You can feel it as you drift through these regions, sensing the diversity of the galaxy. And you realize that each rare star is more than an astronomical object. It is a clue, a piece of evidence, a message from a different era of the galaxy's life. You came here to understand Andromeda more deeply, and now you are beginning to see that its stars are not all the same. Some are ancient elders, some are newborn giants, some are doomed, some are runaway travelers, and some are so intense that they reshape the space around them. These stars gather into vast communities, each with secrets of their own. When you move through Andromeda's vast disk and begin to explore the quieter outskirts, you enter a region where the galaxy's oldest memories are kept, not in books or ruins, but in clusters of stars, dense, ancient communities that act like cosmic fossils. These clusters carry the signatures of events that happened billions of years before humans existed, holding the clues to mergers, collisions, and episodes of star formation long vanished from sight. Astronomers divide these clusters into two main families. The first are globular clusters, tight spheres of stars packed so densely that tens of thousands can live within just a few dozen light years. Many of these clusters are ancient. They formed when the galaxy itself was young, emerging from the turbulent clouds that filled the early universe. Their stars are old, metal poor, and remarkably stable. They drift around Andromeda's halo on wide elliptical orbits, like wandering elders carrying stories of a distant past. The second family consists of open clusters, looser, younger, smaller associations of stars. These are born within the spiral arms, where cool gas collapses into bright knots of star formation. Open clusters tend to be vibrant, blue, and short-lived. Over time, their stars drift apart as gravity weakens, leaving only a faint memory of the cluster that once existed. In the Milky Way, globular clusters are relatively rare. We host about 150 of them, but Andromeda holds more than 500, more than 3 times as many. The number alone reveals something profound. A galaxy accumulates globular clusters through mergers. Each time a dwarf galaxy is swallowed, its star clusters survive the collision, drifting into the halo of the larger galaxy. Andromeda's enormous globular population is proof of a long, chaotic history of galactic cannibalism. It has absorbed many neighbors over cosmic time, and those smaller galaxies left behind their ancient clusters like scattered stones marking the trail. Yet not every cluster in Andromeda fits neatly into the categories astronomers understand. Some clusters contain stars far younger than they should. Imagine finding a teenager living in a retirement community. These clusters appear old and massive, yet when astronomers analyze their stars, they find youthful chemical signatures and unexpectedly bright blue populations. Something happened to these clusters, something that injected fresh gas or triggered a burst of star formation long after the cluster should have gone quiet. These anomalies challenge the idea that globular clusters are simple, single-generation structures. Instead, they hint at histories shaped by mergers, interactions, and perhaps even the remains of smaller galaxies absorbed from the outside. And then there are the extended clusters, objects so unusual that they blur the line between cluster and dwarf galaxy. These extended clusters are larger, more diffuse, and dimmer than typical globulars. They contain fewer stars, but stretch over vast regions. Some astronomers believe they are the stripped cores of dwarf galaxies that lost their outer layers after falling into Andromeda's gravitational field. Others think they formed within the galaxy itself, under unique conditions we don't fully understand. Whatever their origin, extended clusters are rare in the universe, and Andromeda contains many of them. Their presence is a clue pointing toward a violent and complex past. Alongside the extended clusters are the faint, fuzzy clusters, another strange population found almost exclusively in Andromeda. These clusters are loosely bound, dim, and spread out, with stars so widely separated that they barely remain gravitationally connected. Their unusual structure perplexes astronomers. They are too fuzzy to be typical clusters, too coherent to be mere star associations, and too faint to classify easily. Some think they formed in tidal tails created during past mergers. Others suggest they may be the remnants of dissolved galaxies. In either case, faint fuzzy clusters reinforce the idea that Andromeda's halo is a graveyard of past collisions. Moving closer to the disk, you find something even more unexpected. Younger, massive clusters appear in regions where Andromeda should no longer have enough gas to form new stars. These clusters sit in the outskirts or overlap regions between spiral arms, places where star formation should be rare or impossible. Their presence suggests that gas may have been funneled into these regions by past interactions, or that the remnants of dwarf galaxies provided fresh material long after Andromeda's own gas supply began to thin. Chemical mismatches within some clusters add another twist to the story. When astronomers examine the spectra of stars in certain clusters, they find elemental ratios that don't match Andromeda's overall chemical pattern. The stars look foreign. Their compositions resemble those of small galaxies far outside the local group. This mismatch is compelling evidence that these clusters were not formed inside Andromeda, but came from galaxies it consumed. Their chemistry is a message from those vanished worlds, carried by the stars that survived the collision. Even more compelling are the clusters embedded directly within stellar streams. Long arcs of stars stretching across the halo. These streams are the shredded remains of dwarf galaxies torn apart as they spiraled into Andromeda. The clusters riding along them are like survivors clinging to the remains of their original galaxy, drifting along the path their home once followed. When you see these clusters suspended in the faint light of the streams, you are looking at the final traces of galaxies that no longer exist. Some clusters sit in places where gravity should have destroyed them long ago. They survive in surprisingly unstable regions, resisting tidal forces that should have torn them apart. Their existence raises questions about the structure of Andromeda's gravitational field. Were these regions once calmer? Did a past collision reshape the galaxy's tides, leaving the clusters stranded? Or are these clusters simply more massive and resilient than they appear? Every cluster in Andromeda carries a story. Some stories are simple. Clusters born from gas clouds in the spiral arms, bright and young. Others are tragic, remnants of galaxies that fell into Andromeda's pull and were torn apart. Others still are mysterious, extended clusters, faint fuzzies, or chemically mismatched populations that defy clear explanation. Star clusters are fossils of a galaxy's past, Richard Larson once said, and as you move through Andromeda's collection, you begin to see the truth of his words. These clusters are more than beautiful gatherings of starlight. They are records, archives, time capsules containing billions of years of history. You came here to understand the galaxy more deeply, and in these clusters, you see the mosaic of Andromeda's life, its quiet eras, its violent mergers, its moments of creation. The clusters reveal what the stars alone cannot tell. But stars and clusters are only part of the picture. To see deeper, we must change how we observe. When you look at Andromeda in visible light, you see something beautiful, but incomplete. Dark lanes cut across the spiral arms like long, shadowed rivers. Whole regions of the disk appear muted or dim, hidden behind curtains of dust that block starlight from reaching your eyes. For decades, astronomers thought these dark lanes were simply empty, quiet zones with little happening inside them. But that illusion dissolved the moment we began observing Andromeda in infrared. Infrared light behaves differently from visible light. It moves through dust instead of bouncing off it or being absorbed. Where visible light sees darkness, infrared sees glow. Where optical telescopes encounter barriers, infrared telescopes see straight through. And when the first infrared images of Andromeda were taken, the galaxy didn't simply look clearer, it looked completely transformed. In infrared, the dust lanes that appear dark in optical wavelengths suddenly ignite with brightness. They glow because the dust absorbs starlight, warms up slightly, and re-emits that warmth as infrared radiation. What once looked like cold emptiness becomes a luminous web stretching across the galaxy. These glowing filaments reveal the hidden skeleton of Andromeda, the scaffolding that supports its spiral arms and gathers gas into the dense regions where stars are born. Dust, once seen as a nuisance that obscured the galaxy, becomes a storyteller. It marks the places where hydrogen clouds contract, where gravity tightens its grip, and where future generations of stars will ignite. And because infrared can pierce through those dusty curtains, astronomers can detect star-forming regions long before they shine brightly in visible light. To appreciate the power of infrared imaging, imagine gazing toward Andromeda's core with an optical telescope. You would see a bright, hazy bulge, brilliant but blurred. The brightest parts overwhelm the details, and swirling dust hides the true structure beneath the glow. But when viewed in infrared, the haze dissolves. The core sharpens. You can see the rotating stellar disk around the supermassive black hole, a structure that optical light cannot reveal. Instead of a glowing blob, the nucleus becomes a dynamic engine, full of texture and motion. Infrared doesn't just help us see the core. It helps us find the old red giant stars that populate Andromeda's disk and halo. These stars shine brightly in infrared, allowing astronomers to map their distribution far more accurately than visible light ever could. And because red giants act like milestones in a galaxy's history, identifying them is crucial to reconstructing its past. In infrared, the patterns of these stars become clearer, showing streams, arcs, and tidal tails, structures shaped by ancient mergers long hidden behind dust. Some of the most surprising discoveries came when astronomers realized that many features once thought to be voids were filled with stars. Entire regions that looked dark and empty in optical images revealed dense populations of old stars glowing faintly in infrared. These discoveries challenged long-held assumptions about Andromeda's structure, showing that dust had been hiding far more than anyone suspected. Infrared imaging also uncovered tidal tails, long, faint streams formed by gravitational interactions with smaller galaxies. These tails contain stars and clusters drawn out during mergers, and they loop around Andromeda in graceful arcs. Many of these structures were nearly invisible before infrared observations revealed them in stunning detail. The halo, once thought to be diffuse and quiet, suddenly burst into view as a rich landscape filled with remnants of collisions. Another breakthrough came from infrared surveys searching for brown dwarfs, the failed stars that glow too faintly for optical telescopes to detect. Brown dwarfs emit most of their light in infrared wavelengths. Using instruments like WISE and Spitzer, astronomers discovered populations of these objects scattered throughout the galaxy. Their presence helps explain the distribution of mass in Andromeda and provides clues about star formation efficiency across different regions. The past decade brought remarkable progress, but 2025 stands out as a milestone. This year, astronomers released the most detailed infrared map of Andromeda ever created, using data from JWST, Spitzer archives, and new WISE calibrations. Scientists stitched together a far more complete view of the galaxy than previously possible. The map reveals temperature gradients across the disk, showing exactly where dust is warm, cold, dense, thin, or enriched with carbon molecules. Infrared allows astronomers to measure the temperature of dust with remarkable precision. Warmer dust glows more strongly, indicating regions heated by young stars or active star formation. Cooler dust marks areas of dense gas waiting to collapse. These temperature maps function like weather charts for the galaxy, showing the flows and currents of material across hundreds of thousands of light years. With infrared, the galaxy feels alive. It breathes. It evolves. It reshapes itself in ways visible light alone could never show. One of the most impressive achievements of infrared astronomy is its ability to reveal structures that challenge old models. For example, some regions of Andromeda appear chemically older than the dust around them. Others display oddly shaped clouds, suggesting past interactions with dwarf galaxies that left no visible trace except in the infrared glow. These patterns deepen our understanding of the galaxy's complex past, showing that Andromeda's evolution has been anything but smooth. Infrared light is the key to seeing the universe as it truly is, Edward Wright once said. And nowhere is that truer than in Andromeda. When viewed through infrared, the galaxy becomes transparent. You can see its bones. You can see its old stars, its young stars, its hidden streams, and its dusty corridors. You see the complete story, not just the parts that shine in visible light. By peeling back the layers of dust, infrared imaging completes the multi-wavelength portrait of Andromeda that astronomers have been building for decades. The optical view shows beauty. The ultraviolet view reveals the heat of newborn stars, but the infrared view shows truth. It shows the structures that hold the galaxy together and the hidden processes shaping its evolution. And now that we can truly see Andromeda, we can finally ask what shaped it. When you look at Andromeda today, with its elegant spiral arms, its glowing core, and its calm halo, it's easy to forget that galaxies are not born in peace. They are shaped by violence, sculpted by encounters that span billions of years, and rebuilt atop the ruins of what came before. Andromeda is no exception. In fact, when astronomers study its outer regions, they find unmistakable evidence that this galaxy once endured a dramatic collision, one powerful enough to change its size, structure, and future. The first hints come from the stellar streams that stretch across Andromeda's halo. These streams are long, faint rivers of stars looping around the galaxy in delicate arcs. They look graceful from afar, but their origin is anything but gentle. Stellar streams form when a smaller galaxy is torn apart by gravity as it spirals inward. Over millions of years, its stars are pulled into thin trails that wrap around the larger galaxy. Andromeda has many such streams, and some of them are enormous. One of the largest wraps so far around the halo that it looks like the ghost of a lost galaxy, still circling long after its core has vanished. But the streams tell only part of the story. The motions of halo stars provide the second line of evidence. When astronomers measure the velocities of stars in Andromeda's outer halo, they find patterns that don't match those of a calm, undisturbed galaxy. Instead, some stars move in coordinated groups, all sharing similar orbital directions or speeds. These stars weren't born in Andromeda. They came from a galaxy that merged with it, a galaxy whose stellar populations still move together even after billions of years. The halo itself isn't symmetric. When scientists create 3D models of its shape using red giants and variable stars as tracers, they find that the halo of Andromeda is warped stretched, and uneven. Parts of it bulge outward. Other regions dip inward. This kind of distortion doesn't happen on its own. It takes a massive gravitational encounter to twist a halo so dramatically. Gas clouds provide yet another clue. Some clouds in Andromeda move in ways that make no sense if they originated within the galaxy. They travel at odd angles or at speeds inconsistent with the rotation of the disk. Their chemical compositions differ too, carrying ratios of elements that don't match Andromeda's typical patterns. These clouds are refugees, remnants of another galaxy that collided with Andromeda and left behind scraps of its interstellar medium. Taken together, these clues paint a striking picture. Andromeda did not simply consume small dwarf galaxies. It likely absorbed a galaxy larger than the Large Magellanic Cloud, possibly even comparable in size to a full mid-range spiral. The chemical mismatches, velocity anomalies, and spatial distortions all point toward a major merger event, not just a series of small collisions. This idea is supported by the structure of Andromeda's bulge, the bright, dense region at its center. Andromeda's bulge is unusually large, much bigger than the Milky Way's. Large bulges often form when massive galaxies collide. The gravitational forces funnel gas toward the center, triggering intense bursts of star formation and building up a thick, bright core. In Andromeda, the bulge shines as a monument to an ancient cosmic impact. These starburst cycles are another key piece of the puzzle. After a major merger, a galaxy undergoes a period of frantic star formation as gas clouds collide, compress, and ignite. For several 100 million years, new stars form at extreme rates. Then the activity settles. The galaxy enters a dormant period. Andromeda shows signs of having gone through exactly these cycles. Some regions contain enormous populations of stars that all formed around the same time, evidence of a starburst that follows a major collision. One of the strangest discoveries is the arrangement of Andromeda's satellite galaxies. Many of them orbit in a single, remarkably flat plane. This alignment is unusual. In most galaxies, including the Milky Way, satellite galaxies orbit in random orientations, scattered like bees around a hive. But in Andromeda, the satellites seem to follow a coordinated path, as though shaped by a single gravitational event. This kind of structure can form when a large galaxy merges with another, creating a tidal field that organizes the orbits of surviving satellites. Piece by piece, the evidence converges. Andromeda's past was defined by violence. It did not grow slowly and peacefully. It grew by devouring galaxies, including at least one impressive in size. The implications ripple outward. A major collision would have shaken Andromeda's structure, thickened its disk, enriched its halo with stars from the absorbed galaxy, and altered the orbits of countless clusters. It would have fed the central black hole, increasing the mass of M31 as it consumed gas and smaller black holes from the intruding galaxy, and it would have permanently changed Andromeda's future trajectory, including the one that eventually will lead it into a merger with the Milky Way. You came here to understand the galaxy more deeply, and now you can see its past written in every distorted stream and chemically mismatched star. Andromeda is not simply a serene spiral drifting through space. It is a survivor of cosmic turmoil, reshaped, expanded, and transformed by the galaxies it has consumed. Galaxies are built on the ruins of their predecessors, Abraham Loeb reflected. And when you look at Andromeda, you are seeing those ruins, woven into its halo, stretched through its disk, and shining faintly in the streams that circle its core. These signs of ancient collisions reveal why Andromeda is so massive and why its structure is so unusual. But the greatest transformation of all is still in the future. When you look at a full image of Andromeda, bright, crisp, beautifully structured, it's easy to forget just how impossible that image truly is. No single telescope, no single exposure, no single night under the stars can capture a galaxy this enormous. Andromeda stretches across 220,000 light-years. Even from where we stand, 2.5 million light-years away. It spills across a portion of the sky 6 times larger than the moon. It will not fit neatly into any camera frame. So how do astronomers reconstruct something this vast? How do they map a galaxy piece by piece until the fragments become a whole? The journey begins with a simple truth. We never see Andromeda all at once. We collect it, we stitch it, we build it. Hubble demonstrated this in spectacular fashion. To create its famous portrait of Andromeda, the telescope had to take thousands of exposures, each one capturing a tiny patch of the galaxy. Astronomers then combined those exposures into a massive mosaic. The finished image became the largest Hubble had ever assembled, containing over 100 million resolved stars. But even that monumental effort covered only a slice of the galaxy's disk. To map all of Andromeda requires even more. More telescopes, more wavelengths, more data than any single mission could gather. This is where modern astronomy steps in. JWST, paired with powerful ground-based observatories, provides a flood of information across multiple dimensions. Not just images, but measurements, distances, using standard candles like Cepheids and RR-Lyrae variables, motions, captured through Doppler shifts and proper motion tracking, chemical fingerprints, read through spectral lines, dust distributions, mapped by infrared and submillimeter telescopes. Piece by piece, these data sets combine into a three-dimensional reconstruction of Andromeda, something far richer than any photograph. Measuring distance is the first step. Without knowing how far away each region is, we can't understand the shape of the galaxy. Cepheid variables help here. Their brightness oscillates with clockwork precision, and the period of their pulsation reveals their intrinsic luminosity. By comparing that intrinsic brightness with what we see from Earth, astronomers calculate their distance with remarkable accuracy. These stars are the cosmic mileposts of Andromeda. RR-Lyrae stars provide another set of markers, especially useful in the halo, where the stellar populations are older. Their predictable brightness variations allow astronomers to map the outer structure of the galaxy, tracing the streams and arcs left behind by ancient collisions. And then there is the tip of the red giant branch. When red giants reach a specific stage in their evolution, they shine with a nearly uniform luminosity. This consistency makes them excellent tools for distance measurement. By locating thousands of these stars across Andromeda, astronomers create a finely detailed depth map, revealing which regions lie closer or farther, rising or dipping in the galaxy's massive disk. Once distances are known, astronomers turn to motion. Every star in Andromeda is moving, Some drift gently through the halo. Others race through the disk at hundreds of kilometers per second. To measure motion, astronomers use redshift, which stretches a star's light if it's moving away, blue shift, which compresses its light if it's moving toward us. Proper motion, the tiny change in a star's position over years or decades. These measurements show how the galaxy rotates, how its halo sways, and how its streams orbit the core. They reveal the gravitational fingerprint of past mergers and the future path toward the Milky Way. The interstellar gas is mapped differently. Radio telescopes tune to the 21-centimeter hydrogen line, a signature of neutral hydrogen gas. This allows astronomers to trace the cold clouds that drift through Andromeda's disk. Carbon monoxide mapping reveals the denser molecular clouds, the birthplaces of new stars. Dust, too, receives its own treatment. Infrared telescopes like Spitzer and WISE, along with far infrared and submillimeter instruments, track the thermal emission from dust grains. These observations show where the dust is thick, where it's thin, where it's heated by young stars, and where it lies cold and quiet. When overlaid onto the gas maps, the dust structures reveal the galaxy's star-forming engine in exquisite detail. Each dataset is powerful on its own, but when they are layered together, stellar distances, motions, chemistry, gas maps, dust maps, they form something extraordinary, a complete 3D model of the galaxy. It is a model alive with complexity. Some regions rise like mountains, others slope like valleys. Streams weave through the halo. The disk bends and warps. The core thickens and rotates. Every part of the galaxy becomes a coordinate in a vast cosmic grid. Of course, this reconstruction is not perfect. Dust scatters light unpredictably. Foreground stars from the Milky Way sneak into the images. Instrument noise introduces subtle distortions, but with new calibration techniques and cross-correlation between multiple telescopes, these issues shrink year by year. By 2025, astronomers achieved something remarkable: the largest and most detailed dataset of Andromeda in human history. Billions of pixels, millions of stars cataloged, hundreds of thousands of spectra, trillions of calculations performed through machine learning systems designed to recognize patterns too subtle for the human eye. It takes thousands of tiny windows to see a galaxy whole, Jennifer Wiseman once said. And standing before the 2025 mosaic, you can feel the truth of her words. Each exposure is a window. Each wavelength is another. Each survey adds a contour, a shadow, a new layer of meaning. Together, they reveal a portrait of Andromeda that humanity has never seen before. Sharper, deeper, richer, and more complete. And yet, even this masterpiece is still only a version of the galaxy, a translation of reality into something our eyes and instruments can understand. The universe itself is always more complicated, more layered, more elusive than any model can capture. But now, more than ever before, humanity holds a true map of Andromeda, a map built from cross-woven data, from thousands of nights of observation, from telescopes orbiting Earth and resting on mountaintops. And this map does more than reveal the past. It points to the future, a future shaped by gravity, a future that binds Andromeda and the Milky Way together. And what this map reveals is a destiny written in gravity. You've spent this journey moving through Andromeda's past, and present. Its stars, its dust, its collisions, its quiet mysteries. But now, you arrive at the part of the story that reaches forward. Not millions of years, but billions. Not a chapter of Andromeda alone, but a chapter shared with us. Because our galaxies are on a path that gravity has already written. And one day, long after our sun has lived most of its life, Andromeda and the Milky Way will meet. Right now, Andromeda is moving toward us at about 110 kilometers per second. That number sounds fast, but on cosmic scales, it's gentle. It is the slow, steady pull of gravity between two massive galaxies drifting inside the same region of the universe. And it surprises many people because the universe itself is expanding. Galaxies everywhere are moving away from each other as space stretches. But gravity works on a different scale. Where mass is concentrated, expansion loses its grip. Andromeda is close enough and massive enough that gravity overpowers expansion. The two galaxies fall toward each other like distant islands drifting across a quiet sea. The collision won't happen soon. 4 to 5 billion years stand between now and that moment, but the interaction has already begun. Both galaxies are surrounded by enormous dark matter halos, vast spheres that extend far beyond the visible stars. These halos overlap long before the disks touch. And when halos overlap, gravitational tides begin to act across unimaginable distances. The story of the merger has already started. Astronomers describe the future collision in a series of stages, built from detailed simulations and updated with the precise measurements gathered in 2025. First approach. Andromeda draws closer, its disk slowly shifting in our night sky. Over millions of years, it grows larger, brighter, more stretched. The dark matter halos pass through each other almost silently, but their gravity begins to twist the outer regions of both galaxies. First pass. The galaxies make their first close sweep. They don't crash like solid objects. They pass through each other like two clouds of stars. Tidal forces pull out long, graceful arcs. Some of the spiral arms stretch into enormous tails. Others warp and twist. Gas clouds collide, compress, and ignite a burst of new star formation, tidal distortion. After the first pass, the galaxies drift apart slightly, but remain locked by gravity. Their shapes distort even more. The disks tilt. The bulges swell. Streams of stars trail behind them like cosmic ribbons. Second pass. Gravity drags the galaxies back together. This time, their centers spiral inward. The cores dance around each other in tightening loops, shedding energy with every orbit. Full merger. The nuclei finally combine. The stars of both galaxies mix. The disks dissolve. The structure settles into something new. Neither Andromeda nor the Milky Way. Relaxed elliptical galaxy. After hundreds of millions of years, the chaos fades. What remains is a single giant galaxy, rounder, more massive, filled with old stars, and a new generation born from the collision. Astronomers call it Milkomeda, but long before that final stage, the sky above Earth transforms in ways difficult to imagine. Picture the night sky 2 billion years from now. Andromeda is no longer a faint smudge. It spans a width greater than the full moon. Its spiral arms are visible to the naked eye. Over time, the galaxy grows so large in the sky that it becomes a luminous structure stretching across the entire horizon. Its core brightens into a glowing sphere. The spiral arms begin to warp. Their elegant curves distort. stretching into long plumes as tidal forces twist them apart. Imagine standing on Earth and seeing an entire galaxy loom above you, an arc of light tens of degrees wide. It would be the most spectacular sky any human being has ever seen. And if a future civilization survives long enough, they may look up and watch galaxies intertwining like streams of starlight. What happens to our sun in all of this? The answer is both comforting and humbling. The chance of the sun colliding with another star is incredibly small. Even when two galaxies merge, stars remain separated by vast distances. The sun will move through the new gravitational landscape, but it will not collide with another star. But its orbit can change. As the galaxies merge, gravitational forces may kick the sun outward, inward, or into a slightly different path. It could find itself in a new neighborhood, perhaps farther from the center of the merged galaxy, perhaps closer. Earth will move with the sun. Our planet will not be torn apart. It will simply follow whatever new orbit the sun settles into. The dark matter halos of both galaxies pass through each other as well, shaping the merger. Because dark matter does not collide like gas, the halos glide through, overlapping, and then stabilizing into a new structure that dictates the final shape of Milky. The merger brings both challenges and opportunities. Gravitational kicks could perturb orbits. The starburst triggered by colliding gas clouds could bathe regions in bright ultraviolet light. But the same process also enriches the galaxy with heavy elements, fueling new generations of stars and potentially new planets. Collisions between galaxies do not destroy the universe, they recycle it. The final result, according to simulations refined with 2025 data, is extraordinary. Milky will be massive, bright, and elliptical-like, with a large central bulge and a halo filled with stellar streams from both progenitor galaxies. The orbits of surviving clusters will reveal the history of the merger, and the combined supermassive black holes, M31s and Sagittarius A, may eventually spiral together to create a single, enormous black hole at the heart of the new galaxy. The 2025 dataset played a key role in refining our understanding of this future. Velocity measurements allowed astronomers to model the timing of the merger with greater accuracy. Halo shape reconstructions revealed how the dark matter envelopes will interact. Proper motion tracking allowed a clearer picture of Andromeda's approach path. These refinements sharpened the future like a focus dial, turning slowly but steadily until the image becomes clear. And the most extraordinary part? If humanity or any descendant civilization survives 4 or 5 billion years, surviving climate change, surviving technology, surviving its own evolution, they will witness a sky unlike anything alive today can imagine. A sky bright, strange, and beautiful. A sky filled not with a single galaxy, but with two spiraling into one another. A sky that reflects our place in a universe always in motion. Galaxies don't collide like cars. They merge like clouds, as Avi Loeb once said. They drift together, pass through each other, stretch, mix, and settle into something new. And the Milky Way and Andromeda are no exception. You came here seeking calm, understanding, and perspective. And now you know that even on cosmic scales, nothing is fixed. Everything moves. Everything evolves. Everything joins and reshapes into something larger. But the future is only half the story. What about life caught in the middle? When people imagine two galaxies merging, they often picture destruction, stars smashing into each other, planets being torn apart, civilizations wiped away in a moment of chaos. But that picture isn't true. A galactic merger is dramatic, yes, but not apocalyptic. It's slow, gentle in many places, violent only in specific regions, and full of possibilities far more nuanced than a single story of ruin. In reality, a merger is not the end of life. Sometimes, it is the beginning of conditions that make life even more likely. As Andromeda and the Milky Way drift toward each other across billions of years, most regions in both galaxies will remain calm. Stars are so widely separated that even during a merger, the chance of collision is almost non-existent. Space is mostly empty, and that emptiness protects worlds far more effectively than people imagine. A planet can move through this process without ever encountering another star, or even a thick cloud of gas. Of course, not every region will remain untouched. The gravitational tides between the galaxies will ripple outward like waves through water. Planetary systems near areas of strong tidal influence might experience orbital shifts. A star's path could be nudged. A planet's year could lengthen or shorten. Some systems may become unstable, not because of direct collisions, but because even tiny gravitational changes can alter long-term dynamics. Some planets may drift closer to the dense, star-bursting regions, where new stars ignite from compressed gas clouds. These regions are vibrant, young, and crowded. For such planets, the sky would glow with the light of newborn stars. But with beauty comes risk. More stars means more debris, more stray asteroids, more passing objects that could interact with the system. A once stable environment could become unpredictable. Yet the opposite is also true. Some planetary systems may be pushed out of chaotic regions and into quieter neighborhoods. Gravitational kicks can send stars drifting into calmer orbits, away from dense galactic intersections. A world that once orbited near active star-forming regions may find itself in a quieter stretch of the merged galaxy, a place ideal for long-term stability. This dual nature is one of the most intriguing aspects of a galactic merger. Not all change is dangerous. Some of it is protective. What about civilizations? If intelligent life emerges, or still exists, billions of years from now, the merger will not be a singular catastrophe. Instead, it will unfold slowly enough that entire cultures could watch it happen generation after generation. The changing sky would become part of their mythology, part of their science, part of their understanding of the universe. Civilizations experiencing instability, perhaps due to shifting planetary orbits or increased asteroid encounters, might migrate towards safer regions. Spacefaring cultures could relocate to calmer pockets of the galaxy or to promising young systems forming in the merger's aftermath. A galactic merger spreads opportunity as much as it spreads disruption. And for civilizations already thriving in calm regions, the merger may barely affect them at all. They would simply look up and witness a breathtaking sky, watching Andromeda stretch, distort, and mingle with the Milky Way. For those who survive to see it, the night sky would become the greatest cosmic show in their species' history. A slow dance of star systems painting arcs across the heavens. From a biological perspective, mergers create fertile environments. When galaxies collide, star formation surges. gas clouds compress, metals become more abundant, and young stars fill the sky. These new stars form planetary systems, and with higher concentrations of heavy elements, those planets may be rich in the raw materials needed for life. On worlds that orbit these new stars, life may emerge for the first time, simple at first, then growing in complexity over billions of years. Life thrives in diversity, and mergers create diversity on a galactic scale. Different environments, different temperatures, different radiation levels, different chemical mixtures, all the conditions life needs to adapt, evolve, and spread. The chaos of a merger does not erase the possibility of life. It multiplies it. You can imagine a future in which descendants of humanity witness the rebirth of their galaxy. Perhaps they stand on a world far from Earth. Perhaps they live in orbiting habitats. Perhaps they have transformed into something we cannot imagine. But if they endure, they will watch the Milky Way's familiar shape dissolve and then reform into Milkometa, a galaxy brighter, more massive, and full of fresh stars. In some regions, planets may be nudged from their stars and drift as lonely rogues through the darkness. Yet even these worlds might harbor warmth through internal geology or thick insulating atmospheres. Life could continue in deep oceans beneath ice. The universe rarely offers simple endings. A merger is not something life must fear. Life adapts. Life shifts. Life searches for stability and finds it again and again across cosmic time. Even on Earth, life has endured asteroid impacts, mass extinctions, atmospheric transformations, and continental upheavals. A galactic merger unfolds far more slowly and far more gently than any of those catastrophes. Life doesn't resist the universe. It adapts to it. Stephen Hawking once said. Those words echo across this future era. In the vast timeline of the cosmos, life's resilience is one of the most remarkable forces at play. And so, as Andromeda and the Milky Way evolve into something new, life will continue, shifting, transforming, finding pockets of warmth and stability wherever they exist. Some civilizations may fall, others may rise. Some may drift into the quiet outskirts of the merged galaxy, continuing ancient traditions under new skies. Others may explore the starburst regions, seeking opportunity among the freshly forged systems. A few may migrate into intergalactic space, using the energy of the merger to propel themselves into the darkness between galaxies. This future is not a tragedy. It is a transition. From chaos comes order. From destruction comes creation. From an ending comes the beginning of something larger. And standing at the crossroads of these futures, you realize the deeper truth. Galaxies change. Stars change. Worlds change. And life, in all its forms, flows with that change. It bends. It adapts. It endures. And with that, our scientific journey reaches its quiet horizon. When you look back across everything Andromeda has shown you, the stars, the dust, the collisions, the quiet pockets of survival, you begin to realize that this galaxy isn't just a distant object floating in the darkness. It is a long, slow conversation about time. A conversation happening across 2.5 million light years, whispered through starlight that began its journey long before our species existed. And in that whisper, there is a lesson meant not only for astronomers, but for anyone who has ever felt overwhelmed by the pace of life. Across its history, Andromeda has changed in ways both subtle and violent. Nebulae have collapsed into brilliant blue clusters. Ancient red stars have slowly burned down toward stillness. Tidal streams have been pulled apart by gravity. Whole galaxies have fallen in and dissolved into its halo. Nothing inside Andromeda has stayed the same. Not the stars, not the clusters, not the orbiting streams that circle its core. And yet, in the end, the galaxy continues on. It finds new balance. It becomes something new without losing what it once was. And that rhythm mirrors our own lives more closely than you might expect. We tend to imagine galaxies as steady, unchanging structures, eternal spirals frozen in space. But Andromeda proves the opposite. It has weathered collisions fierce enough to warp its halo. It has survived long eras of intense star formation when radiation flooded its spiral arms. It has absorbed galaxies far older and far younger than itself, each one adding new stars, new elements, new memories. Every stream of stars stretched thin across its halo is a reminder that nothing, even on cosmic scales, remains untouched by time. And if a galaxy can live through such transformations, then perhaps the turbulence in our own lives is not a flaw, but a natural part of the story. 2.5 million light years of starlight teaches you something about patience. Andromeda does not hurry. When something breaks, it takes millions of years to mend. When something changes, it lets the change pass through slowly. A tidal stream pulled from a dwarf galaxy may take 1 billion years to settle. A disturbed region in the disk may need hundreds of millions of years to regain its spiral shape. Andromeda moves at the speed of gravity, not the speed of urgency. And somehow, that brings comfort. Because if the universe itself is willing to take its time, maybe you can too. Think about the stars and clusters scattered across Andromeda's halo. Those faint remnants of galaxies it once consumed. Many of them are not arranged neatly. Their paths are crooked. Their motions are messy. Their chemistry doesn't match the patterns around them. They are imperfections, scars, evidence that even the universe doesn't always create smooth or symmetrical outcomes. But those imperfections shine. They are some of the most informative, beautiful structures in the galaxy. They tell us how Andromeda grew, how it changed, and how it survived. And somewhere in that truth is a message for anyone listening at the end of a long day. You are allowed to carry the marks of what you've been through. You are allowed to be reshaped. You are allowed to not look exactly like the version of yourself you once imagined. Because even galaxies do not stay perfect. Even galaxies lose things and find new things and begin again. From chaos, Andromeda forms new stars. From collisions, it forges the heavy elements that make planets possible. From the debris of what once was, it builds the materials for what will be. The same universe that produces destruction is also the one that produces renewal. And here you are, listening in the quiet of late 2025, after a year that may have pressed on you in ways no one else can see. Deadlines, responsibilities, changing plans, a life that shifts faster than you can always keep up with. But above you, Andromeda drifts in silence. Its light has traveled millions of years to reach your eyes, carrying a reminder that nothing in the universe moves as quickly as we think it should. If the universe can wait billions of years to find balance, you can give yourself a moment, a night, a breath. You are not meant to hurry through everything. You are not meant to solve all things at once. Time in the universe is generous. It flows slowly, patiently, allowing space for things to fall apart and come back together again. We are a way for the cosmos to know itself, Carl Sagan said, and that includes knowing its rhythm, its quiet patience, its long arcs of healing, its capacity for renewal. As you reflect on the story of Andromeda, you begin to understand your own story a little more clearly. You are small in the cosmic sense, yes, but not insignificant. Your life, your breath, your worries, your hopes, they all exist inside a universe that is vast enough to contain them. You are temporary, but that temporariness is beautiful. It allows you to change, to grow, to become something new over time, just as Andromeda has. Andromeda teaches you that even chaos becomes beautiful over time. It teaches you that endings are beginnings stretched across a much larger timeline. It teaches you that nothing is wasted, not light, not time, not experience. And as your thoughts settle and the pace of your breathing softens, you feel the shift from curiosity to calm, from cosmic wonder to quiet meaning. The galaxy becomes less of an object you're studying and more of a companion reminding you to take things slowly. And as we drift toward the end of our journey, the universe becomes very quiet. As you come to the end of this journey, let the image of Andromeda drift slowly away in your mind. Not abruptly, but gently, like a distant lantern carried down a dark, quiet river. The faint glow of its stars begins to soften, dissolving into the surrounding darkness. The spiral arms that once stretched wide across your imagination start to fade, their outlines blurring into something dreamlike, almost weightless. Even the dust lanes, sharp and dramatic when we first encountered them, now appear as soft, delicate strokes, like charcoal brushed lightly across a page. You can picture the galaxy turning, but so slowly that motion becomes a kind of stillness. At the center sits M31 Nas, the enormous supermassive black hole, its gravity steady and unwavering. But tonight, it feels peaceful, like a sleeping heart deep inside a giant. Around it, young blue stars shimmer. Old red giants glow faintly. Clusters drift like quiet islands of light. Everything is moving, but nothing is rushing. Let that feeling sink in. Everything is moving, but nothing is rushing. You've traveled far to reach this moment. Across models and history, across clouds and collisions, across invisible forces and unimaginable spans of time. You have seen how astronomers debated Andromeda for generations, unsure whether it was a nebula or an entire island universe. You learned how its structure comes together in layers of stars, gas, dark matter, and dust. You peeled back those layers with infrared light, revealing the hidden machinery that lies underneath. You met its rare and restless stars, blue variables that flicker unpredictably, Wolf-Rayet stars burning their lives at impossible temperatures, magnetars trembling with fields stronger than anything on Earth. You explored clusters ancient enough to remember the early universe and streams of stars that stretch like faded memories pulled across the sky. You stepped through collisions that reshaped the galaxy and watched its future unfold as it drifts toward the Milky Way. And you looked at life, not just here, not just now, but in all the places where life might bloom during and after a galactic merger. You discovered that even across the greatest transformations the cosmos can offer, Life is not erased. It adapts. It searches for calm. It finds new worlds, new environments, new beginnings. And now, as you look back on Andromeda's story, you realize something important. The universe is not as frightening as it seems from far away. Even when galaxies collide, they do so in silence. Even when stars tear through tidal streams, the motion is smooth. Even when black holes merge, the ripples spread gently through space and time. The universe is vast, but it is not chaotic. Not in the way our days sometimes feel chaotic. It unfolds slowly, gracefully, guided by laws that do not hurry. Right now, in this quiet moment, you are safe within that slowness. Andromeda can move toward the Milky Way for billions of years without threatening a single day of your life. Everything you've seen, every collision, every burst of star formation, every drifting cloud, happens at a pace so slow that no sound is ever made. No impact shakes the night sky. No drama interrupts the stillness you live in. Feel the weight of that. Let it settle your breathing. Let your thoughts loosen just a little. The universe is slow. And tonight, you are allowed to slow down with it. You may be sitting with the last hours of 2025 on your shoulders, emails waiting, responsibilities stacking, decisions pressing. You may feel the weight of a year that moved faster than you expected, but the universe doesn't ask you to keep up with it. It never has. It moves at the speed of light stretched across millions of years. It moves at the speed of patience. You don't have to solve everything tonight. You don't have to carry every worry into your dreams. Right now, all you have to do is rest. Let the pace of the universe become your pace for a moment. Let the quiet between the stars become your quiet. Remember that the light from Andromeda took millions of years to reach you. It crossed empty space in complete silence. It traveled past dead stars, new stars, invisible dust, lost galaxies, and drifting planets, all to arrive softly at this moment, in your room, in your breath, in your ears. If a beam of starlight can take its time, then so can you. Imagine, just for a moment, that you are floating between the Milky Way and Andromeda. Both galaxies hang in the darkness, like two great ships drifting across a calm ocean. Their lights shimmer. Their halos overlap softly. They move, but only with the gentlest pull of gravity. Two giants drifting toward a distant future neither needs to hurry to reach. That's the truth of the universe. It is wide, it is ancient, it is calm, and you belong to it. You are small? Yes, but you are part of something vast, part of something old, part of something patient and quiet. The universe is under no obligation to make sense to you, Neil deGrasse Tyson once said. But that's the gift of nights like this. You don't have to understand everything. You don't have to analyze every detail. You don't have to solve the mysteries of the cosmos. You only have to feel its stillness and let that stillness ease you into rest. Let the galaxies drift. Let the stars burn softly. Let the darkness hold you. Tonight, the universe is quiet, and so are you. Good night, traveler. Until our next cosmic journey.